Hello, my name is Mustafa Khan. Today I'll be presenting the design, fabrication, and testing of the wire arc additive manufacturing done by my group of engineers at Rochester Institute of Technology, Dubai. Before I begin with what the project is about, let us address the issue at hand. Though here in the Gulf countries, when it comes to the construction business, they usually tend to have significant amounts of material wastage and labor costs and so on. They need a better solution to these set of problems. The solution is, after much research conducted by my team, we figured that 3D printing technology will cut labor costs up to 50% and waste production up to 60%. We have three main additive manufacturings in metals. The first one being the electron beam, the second one being the laser selective melting, and the third one being wire arc. Our focus is entirely on wire arc. The value this technology brings to both the research community as well as the industry is one, limited resources are needed for its fabrication, and two, it's an innovation in the field of manufacturing processes. Moving forward, we have our CAD model for the wire arc system. It includes a CNC which will hold the blowtorch. There's also a print bed that is assembled with the CNC to ensure stability for the Waam system. The cylinder is kept beside the print bed. It is responsible for providing inert argon gas, which in turn acts as a shield against any impurities that might damage the printed material. Here is a CAD model showcasing the entire dimensions of the entire system. This is a very important component of our project, the torch holder. Our team had to come up with many designs. Designing this was actually a challenge because we had to ensure the printing angle of the blowtorch was kept constant. Moving forward to the finalized parts list. The first one we have is a Millermatic Passport Plus. This is the blowtorch system. It also comes with a M10 gun, which happens to be the blowtorch itself. We also have the motor drivers 6600, which are responsible for sending signals to the motors inside the CNC. The CNC motors themselves, they're called NEMA 23. They happen to carry a torque of 2.2 newtons per meter. We also have a power supply of 12 volts and an upper nut of 8 millimeters. Next, we have an Arduino. This is the microchip controller. We usually feed inputs to Arduino, which ends up controlling the CNC. We have a mild steel print bed, and then we also have a chromium bars, which have negligible tolerance. Our team actually ended up importing them from Turkey, as local markets just couldn't provide the necessary tolerance that we were looking for. Next we have is the electrical setup. Here you can see that the Arduino is actually connected to the motor drivers, and they in turn are connected to the motors themselves. The Arduino is going to be connected to our computer system. So this diagram basically shows the chain of command for the mechanical setup as well. Here we have the GRBL. This is our software program. It is basically like a language library used for the Arduino. Next we have is the universal G code. This is the program that actually takes digital CAD models, splices it into layers, and translates it and puts them in a mechanical input and sends it to the motor drivers. This is an integral software, as this would be the main program that will be converting our digital model into mechanical commands for the motors. Moving forward towards the calculations, we are dealing with two main calculations, the first one being the welding volume, and the second one being the heating input. With the first equation, we know that if the diameter of the wire that is being fed into the system, if it's increased, the weld volume will increase as well. If we increase the weld volume, it will also we will also have to decrease the welding speed along with it, and this is showcased in the table below. Our second equation relates to the linear heat input with voltage, current, and as well as welding speed. Since we're relying on the atmosphere to cool down our specimen, we want our H value to be small. Hence, as voltage is directly proportional to current and heating input, we would want to work with a optimum level of voltage and current and high welding speed. Moving forward towards the manufacturing, here is the mild steel print bed. This is used to complement the CNC, and CNC will be assembled on top of this. Here's the CNC setup. Moving forward towards the testing phase, the figure shows the longitudinal and transverse orientation of a stainless steel specimen. The stress strain curves are shown in the second figure. This shows that small changes in the orientation actually change the properties of the material. This was actually our team's goal to figure out the best possible results using our system. We actually, in the testing phase, we wanted to complete compression tests in our fabrication lab. And we wanted to do that by playing around with these three main variables: the feed rate, the step size, as well as the acceleration. And unfortunately, due to the global pandemic taking place, we were forced to provide a proof of concept. Moving forward, we have a proof of concept, which shows the working mechanism of this project. Here it is. So what we have done is we've replaced the pencil instead of the blowtorch because we actually wanted to test the accuracy of the machine itself. We've set some inputs through the Arduino using our computer, and it's taking those inputs from the Arduino straight into the motors. Thank you.